talk is modularity of minimal universal deformation rings.
Thank you very much. Today and tomorrow in my two talks, I will try to prove the main conjecture, main theorem, as described by Ken, in the minimal case. And I apologize for repeating some of what Ken did in the first half of today's talk. First, because I want to emphasize a few points, and the other reason is that I do have, and it becomes crucial to consider a certain gamma 1 level structure, which Ken didn't consider. So let's write the goal, show that the map that Ken just described between the universal deformation ring of type D and the Hecke algebra of type D is in fact an isomorphism. And hand in hand with this goes the fact that these are local complete intersection rings in the minimal case. Now I want to start by saying a few words about minimal. We will say that the deformation is minimal, so rho as a minimal deformation of rho bar, meaning that rho bar being unramified at a certain prime away from P slash flat at that P, if this is the case, we require that rho be the same. So in particular, if rho bar happens to be both Zellmer and flat, both ordinary and flat and at P, we require that the deformation is flat. Now, if you consider rho bar EP and rho EP as a deformation, when will it actually happen that this is, so now we consider E semi-stable. When will it actually happen that this acquires more ramification or at P non-flatness than this one? Well, or put it in the negative, when doesn't it happen? When is this a minimal deformation of this? So rho EP is a minimal deformation if and only if, for all bad L, including P, and here the condition is the same, P does not divide the L-adic valuation of the minimal discriminant of E or of the J invariant or of the Tate period. It's all the same. So you see right ahead what kind of elliptic curves fall into this minimal deformation, but of course not all of them fall into this category. And logically, Weil's proof goes, first he proves this thing in the minimal case, and it will become clear tomorrow when I do the Galois homological arguments based on Washington's talk why it's so important to be in the minimal case. And at a second stage, which will be discussed in Ken's third talk, he sort of compares the discrepancy in the R's and in the T's when you relax the deformation type and proves that these discrepancies are the same and therefore the two rings remain isomorphic. Now one more remark before I start. Wiles gave two proofs of these facts. The first, which is given in chapter 3 of his paper, is that he first, well, needs the fact that this is a local complete intersection, and then, which comes from the Taylor-Wiles paper, and then proves the isomorphism. Then, following a suggestion of Faltings, in the appendix to Taylor-Wiles, they introduced minor modifications to the commutative algebra that were discussed by René in his talk, in his second talk, and managed to prove that this is an isomorphism together with the LCI property. And this is the proof that I will follow, the second proof that is in the appendix. So you will not see the emphasis on the local complete intersection. It will just be a byproduct of the proof. Okay? No. Whoops. I have to practice a lot. Okay. So let us repeat some of what Ken did and write a setup. P will be an odd prime, K will be a field of characteristic P, and we will start with a representation from the Galois group of Q to GL to K, satisfying the following. It is modular. I want to only deal with representations whose determinant is cyclotomic. The deformations will be of the same sort. This makes life easier. And then we have three types of technical conditions. The first one is that the restriction of rho bar to the absolute Galois group of L, where L is the quadratic field of conductor P, Q square root of minus 1 to the P minus 1 over 2 times P, is absolutely irreducible. This is a new condition that you haven't seen so far, and it will become important towards at the very end, actually, of tomorrow's lecture. Although for P equals 3, this kind of condition has another significance. But and then we have, so that's a global condition on the representation, and then we have the conditions that were discussed by Ken. First of all, the restriction to the decomposition group at P is either flat in the sense of Conrad, in other words, comes from a finite flat group scheme, whether supersingular or ordinary doesn't matter, or Zellmer in the sense that it can be written as omega psi inverse star psi 0, where psi is unramified characters. This is what Ken discussed, except that since the determinant is omega, I write it in such a way rather than alpha and beta. But since I included the flat case here, by Zellmer I always mean Zellmer and non-flat. And perhaps you remember from Gross' talk that this condition means exactly that this star here is très ramifié in the sense of cell. In other words, I'll remind you, of course, psi is unramified, omega is tamely ramified, but if you restrict this representation to the wild inertia, you have 1 and 1 here, so you get, and that's an extension of type P, and it's obtained by Kummer theory, and the condition is that it's obtained by extracting P roots of units, of non-units to be très ramifié. Okay, and at L different from P, we assume that rho bar is of the shape omega chi inverse chi, basically the same shape, star, where chi is unramified. And this is what Wiles calls type A. So here are some remarks before we go on. First of all, as we noticed several times before, semi-stable elliptic curves give rise to representations that have this shape at the local decomposition groups. The second remark is that this restriction is not very far from being absolutely irreducible. Of course, it implies that the whole rho bar is absolutely irreducible. But in fact, if the rho bar was absolutely reducible, but its restriction to GL was reducible, then it's easy to see that it must be dihedral and therefore has image of order prime to P. But together with these local conditions, if the image has order prime to P, in fact, you do not have ramification at L, and you are flat at P. So by Ribot's theorem of lowering the level, we arrive at a contradiction. So thanks to Ribot's theorem and lowering the level, this, in fact, is just the same as assuming that rho bar is absolutely reducible. Now, of course, Wiles is more general. He's not assuming that the determinant is omega. And at L's different from P, he's assuming type A or type B or type C, which I will not discuss because they leave very little extra, and even this little extra was finally removed by Fred Diamond, so he will speak about the generalizations of this type A condition, and anyhow, for elliptic curves, this is enough. The last remark that I want to say is that, in fact, psi and chi are quadratic characters. So remark, psi squared equals chi squared equals 1. Well, chi if L is ramified. Of course, if L is not ramified, then you can have any two eigenvalues. But if L is ramified, this chi squared is 1. And the reason, well, I'll better explain it for L. For L, it's very easy because, you see, if chi is unramified, omega is unramified, so the only ramification that you get at L, if ramified, is from the star, so it's tame ramification, since L is not P. So you get a two-step solvable extension where the unramified quotient acts on the tamely ramified quotient. Now, anybody who knows local fields knows that this action is via omega. On the other hand, it's an exercise that somebody did already. From such a triangular representation, the action should be via omega chi to the minus 2, this over this. So if omega chi to the minus 2 is omega, chi should be quadratic. So that's a simple explanation. The similar explanation here is a little more subtle. It's a lemma due to Diamond, which you may find in Wiles' paper. Finally, let us write n rho bar for the conductor away from P of rho bar. This is square free, the Artin conductor, just because we're in type A situation. So this is what I wanted to say about the representation rho bar. And now we will consider deformations. And here I have to consider a new type of deformations that in some sense are the key technical tool applied by Wiles. And they rely on an auxiliary set of primes, Q. But before that, let me introduce some notation. Let sigma be the primes where rho bar is ramified. So they're the divisors of the conductor and P. P is ramified since the determinant is omega. And let's choose a discrete valuation ring O and lambda, as in the previous lecture, such that O model lambda is K. And let us write for D, the deformation type will consist of sigma, the set that Ken was referring to as S, maybe O, and either the word flat or the word Zellmer, depending on the situation for rho bar. But I insist that if it's Zellmer and non-flat, because I want to consider minimal types. And the key technical point is the introduction of a certain set Q, Q1 up to QR, of auxiliary primes, upon which we will put more and more restrictions, and tomorrow at the end we'll have to do some group theory to prove that we can meet all those conditions, all those restrictions. But so far, I want Q to be disjoint from sigma. And I want the Qi's to be 1 mod P. And very important, I want rho bar of Frobenius at Q, which makes sense because Q is disjoint from the ramified primes, to have distinct eigenvalues, which I will call alpha Q and beta Q. In K, well, in case the eigenvalues belong to the quadratic extension of K, then just replace K by the quadratic extension and replace O. Okay, and the definition is a deformation of type dq of rho bar is rho from, let me write G sigma union Q for the maximal Galois group of the rationals, which is unramified outside sigma and Q, and these auxiliary primes Q, to GL2 of some R, let me call it a C ring following Mazur's terminology, the kind of ring we've been considering all the time. And it should satisfy that, first of all, rho mod, the maximal ideal of R is rho bar, that the determinant of rho is epsilon. I want to fix the determinant. That if D is flat, then rho flat, in the sense discussed by Conrad, that any finite quotient, any Artinian quotient of R gives rise to a representation that's associated to a finite flat group scheme. And if D is Zellmer but non-flat, then I want rho to be Zellmer. And in this, well, Zellmer and flat have the same definition as for K, as Ken gave, same shape. And no condition at Q. Just it can ramify, no condition at Q. So here are some remarks. First of all, this is going to be a minimal deformation type when Q is empty. Okay, it's not allowed to ramify outside sigma if Q is empty. And the next thing I want to tell you is what happens at the primes Q, those primes that are so far arbitrary. Oops. Well, I got really entangled. So here's a little lemma. At Q in Q, the restriction of rho to the decomposition group is isomorphic, is semi-simple, isomorphic simply to the sum of two characters, phi1 and phi2. And the proof, I'll just sketch the proof. You see, since rho bar is unramified at Q, okay, and Q is not P, it's easy to see that rho is at most tamely ramified. So rho at most tamely ramified at Q. Next, you know that this theorem that I just mentioned, that the Galois group of QQ can be ramified over QQ, morally speaking, is generated by two elements, f and t, with a relation ft, f inverse is t to the q. Well, you have to be a little more careful when you say such a thing, but that's what there is really. And f is a lifting of Frobenius. You first diagonalize f. You choose a basis in which f is diagonal. So diagonal f in the representation row. And then use the alpha q not equal to beta q assumption. And this is exactly what you need if you want to do it, to prove by induction on the nilpotency degree of the maximal ideal of R that the whole representation, in fact, has the right shape with respect to the basis. So you just have to check what happens to T, use this. And then by continuity, you push it from Artinian rings to any C ring. So that's for Artinian, of course, because otherwise the induction doesn't make sense. Okay, now this is very important because we can now define, so this lemma will be used to define a structure of diamond operators acting on any such R, in particular on the universal deformation ring. Oops. Sorry, can I erase this? I started already, so I didn't switch blackboards. I will not erase that part. So corollary is if you let delta Q be the P CELO subgroup of Z mod QZ star. Okay? Now Q is 1 mod P, so that's some group. And you let chi Q be the character which goes first with the cyclotomic character to Z mod QZ star, and then project onto delta Q. And I want also to let delta Q be the product of all the delta Q's, and chi with bold Q, with a capital Q, to be the product of all those little chi Q's. And lambda to be, so this is notation rather than corollary notation. And lambda to be O delta Q, which is a local ring. It's like the Iwasawa algebra in this game. Maybe I'll put a lambda Q in here. The corollary is that phi 1 restricted to inertia at Q, if you look at this phi 1, which is also phi 2 restricted to inertia inverse, of course, because the determinant is unramified at Q. So this goes into 1 plus the maximal ideal of R into principal units, because the reduction is unramified at Q. Factors through this character delta Q, to delta Q, and therefore defines a map of delta Q to your ring, to the units of your ring. Okay, this is simply because delta Q is the maximal pro P quotient of the Blinization of IQ, so it must vector like that. And this is the way by which we will view these diamond operators almost acting on R. We will have to square it for a technical reason. But let me now quote the theorem that Maser explained, that there exists a universal deformation, which I'll simply call RQ rho Q universal of type deformation of type DQ. So what goes into the proof of this theorem is, of course, the absolute irreducibility of rho bar, and also the fact that the conditions that we imposed are quote-unquote conditions in the technical sense described by Maser. So in particular, we can apply this to the universal ring, RQ. Here, maybe I'll write phi1 universal. We can apply this. This is the corollary that I wanted. And this gives a way of delta Q acting on the universal deformation ring of type dq, except that we want to square this action. So put an action of lambda q, if you want, or delta q, that's the same, on RQ, where delta q acts via the square of this thing. Well, maybe I'll simply write phi1 universal square, and it will become clear in a moment why the square. So this is what I want to say. One last observation is that if you denote by AQ, I'll quickly do it here, the augmentation ideal. Wow, it didn't even stop. Okay. Never do things too quickly. Augmentation ideal here. Here. Then, as part of the notation I wanted, then from the universality of those rings RQ, and from the particular shape that the representation at Q has, it's easy to see what's the relation between them, namely RQ modulo AQ RQ is R. Okay, so in one direction you use the universality of R, in the other direction universality of RQ. Let me just mention that so far we don't even know that the map of lambda Q to RQ is injective, for example. I mean, although that will be, it's rather clear, but I'm not claiming it so far. Okay, so far about deformations, and now we have maybe the augmentation ideal. In a group ring you have the augmentation ideal, okay? So all the things generated by delta minus 1, where delta is a diamond operator. The Hecke algebra. Okay, so let me put, as in Kenstock, n, maybe he called it m, equal n rho bar in the flat case, and n rho bar times p in the Zelmer case, and this is still a square-free number. And let's introduce the group gamma q, where without the q it's just gamma 0 n. But with the Q, we do want now a certain gamma 1 structure. So these are all the A, B, C, D in gamma 0 and Q, such that D maps to the prime to P part in Z mod Q Z star, okay? In other words, of course, D is relatively prime to N and Q by Chinese remainder theorem. I don't care what happens at N. And mod Q, I want it to map to the prime to P part. In other words, I leave in the group just the diamond operators that are in delta Q. Okay, another way to say it is that gamma naught NQ over gamma Q is delta Q. Okay, and let denote by T gamma Q the ring of all Hecke operators. So it's the T, it's not the T prime from Kenstock. I will denote them Tn's, and also I will use the more traditional notation of the U's for the primes dividing N and Q. And we have to consider some diamond operators as well. I want a tensor with O already. Now, of course, this is the ring acting on cusp forms, if you want, or in the Jacobian of this of the modular curve associated to gamma q. And I want to emphasize that I don't face, in the minimal case, problems with the distinction between T and T prime, because there are two reasons that Ken or Wiles makes this distinction so important. One is to show that, in fact, the map from R to T is surjective, but we will be able to show it in this case, thanks to the fact that we're in a square free level. The other thing is when you pass from minimal to non-minimal deformations and you want to compare these rings, it's much easier to do it with a reduced ring rather than with a full ring, but I'm just in the minimal case, so let me stick to this nice ring, which is, we know, its localizations will be Gornstein. And I'm going to define now an ideal MQ, ideal generated by what? So let's put all kinds of things. First of all, lambda, okay, the prime of O. Then we put TL minus the trace of Frobenius, of rho bar, of Frobenius at L for L not dividing NQ. Similarly, L, diamond L minus the det of the same thing for L not dividing NQ. Now, I'm mixing here characteristic 0 and characteristic P. This trace is not, strictly speaking, in T, but lifted to anything. And since you put lambda in there, then you don't care about what this lifting is. So that's what I mean by such an expression. And now at Q, or let's first do it at N, we do UL minus chi of Frobenius at L. This was my notation. If L divides N, UP minus psi of Frobenius at P if you're in the Zellmer case. Oh, I need some more space. And UQ minus beta Q for Q in Q. Okay, let me say a few words. First of all, the chi and the psi here are just the chi and the psi that figured in the condition of type A for those L's, or Zellmer for this. This is the lower left corner. Okay, and if you recall Kenstock, I mean, this is a smart thing to do. I mean, if you recall Carayol's theorem, at least here, and here there's an analog due to, I guess, originally Serre-Fontaine and then Wiles. Here you have a choice. How do you choose between alpha Q and beta Q? Remember, these are the two eigenvalues of rho bar Frobenius Q mod P. Well, we already made a choice in choosing there phi1 and not phi2 to define the diamond action. Okay, there I didn't tell you, but there's some arbitrary choice there. The phi1 and phi2 are interchangeable. And beta Q, of course, phi1 and phi2 might be ramified. The reductions are unramified. So beta Q is the value that the reduction of phi2 gets on Frobenius. Phi2 reduction on Frob Q. If you chose phi2 there, you'll take alpha Q here. It's the same. So this is a candidate to be a maximal ideal. Why maximal? Because we equated any Hecke operator to something. The only problem is that it might be too big. It might be the whole algebra. But that's exactly the theory of reducing the level, or if you want, now which one I want? This one down, this one up. The fact that this is a proper ideal is the celebrated theorem, which is very, very important in this context. Otherwise, you will not be able to do minimal deformations, and otherwise the whole machinery breaks down. So, well, there's the extra Q's here. First, you do it with Q empty, and then you show that, thanks to Carayol's theorem, MQ is also a proper maximal ideal. So in this, there are many people behind this theorem, of course, but if you want to see a reference, it's in Diamond's paper in the Hong Kong volume, I think theorem 6.4, just in this shape. Okay, and of course this is the place where the a priori modularity of rho bar is used and nowhere else. I mean, the result of Langlands and tunnel. So let me write T sub Q. So maybe I should have labeled it T sub D sub Q to follow the notation of Ken, but I'll drop the D, the deformation type. T sub Q is the localization of this T of gamma Q at MQ. And let's also write XQ for the modular curve associated with this group, and JQ for the Jacobian. So Ken described very well in the first lecture how to get the representation that I will call rho Q modular from the Galois group of Q into GL2 of TQ. Let me only say that Ken did it by sort of gluing the lambdatic representations, but that was probably because he was working with a T prime. If you work with a T and you have the result that Tilwin described, that the localization of the Tate module of JQ at MQ is free rank 2 over TQ. Remember, this was the main result that Tilwin discussed, the one that is related to the Gorenstein property, and it will show up again later today. Then you know that this rho Q is automatically into what you want. And now, does it have the chance of being a deformation of type DQ? Not really, because the determinant of this is wrong in some sense. It's not a cyclotomic character, but it's a cyclotomic character times the Nabentypus character chi Q. But here is the main theorem. If you modify it a little bit, by dividing by the square root of this Nabentypus character, is a deformation of rho bar. You see, on rho bar you don't see this because this is 1 mod P of type DQ. Hence, there exists a surjective map from RQ to TQ, so I emphasize surjective, of lambda Q algebras. Bringing, I will not complete it, bringing the universal deformation to this rho Q prime, sort of on matrix elements. Okay, now this theorem is checking that this is a deformation of the right type involves at L precisely this theorem of Carayol that Ken was talking about, and at P an analogous theorem that appears in a paper of Wiles, but I think that it has its origins in unpublished correspondence between Fontaine and Serre. I mean, that's what people say. I haven't seen it. But a very similar theorem. And okay, why is this map surjective? Again, the Hecke operators away from the level you get by the argument that Ken said, but also thanks to the fact you're in square free level and you have Carayol's or Wiles' theorem, you see that you get the U's, the Aitken linear operators, as certain entries in the lower right corner of the matrix. So you get all the Hecke operators. And finally, why does it respect the structure of the diamond operators? So recall, diamond operators naturally map to T. That's a Hecke algebra. And the way we map them to R was via the square of the phi1. And again, you use Carayol's theorem to show that this is just the right choice to make this compatible with a diamond operator action. So here we have this theorem. And now the main theorem is that it is an isomorphism. So maybe I'll spend some time repeating some of what Ken did, but I think at least this Q is new. So the main theorem is that T, I will drop the Q when I refer to the empty Q. So R, which is R empty, is an isomorphism to T, which is T empty, and they're local complete intersections. And the tool that we're going to use is coming. Whoops, I did it all right. It's coming down. It's the criterion that the Wiles-Faltings criterion that René Skov explained in his second talk. So don't copy this. It's in your notebooks if you were at René's talk or in the... Except, well, let's read it. So we have a situation of R to T is surjective. We know it's surjective already, homomorphism of C rings. T is finite flat over O. That's fine. And suppose there exists some universal number R that's going to depend only on rho bar, such that for all n's, you can get a commutative diagram of C rings which are also algebras over O with S1 up to SR, RQ to R, RQ to TQ, TQ to T, satisfying these conditions. S1 up to SR is just the kernel of RQ to R, similarly with the T's. And then if you look at the kernel from the OS to TQ all the way, call it B, it's contained in the ideal generated by 1 plus Si to the p to the n minus 1, and TQ is free of finite rank over the image of this ring in TQ. And finally, most important, RQ is topologically generated by R elements. Now, this is exactly the way René formulated it, except that he used Rn's and Tn's. The only way n comes into the picture is via this condition here. And I labeled them RQ and TQ because I'm going to use for these Rn's and Tn's the RQs that were produced before with some very cleverly chosen Q. So the idea is, I'll now raise it and bring down the blue one. Well, I don't know how much of it you can see, but maybe we'll bring down this one. So the idea, which is really ingenious, is to apply this with the RQs and TQs constructed above, where Q is cleverly chosen. So I have to tell you a few things about Q. First of all the Qs in Q will now be congruent to 1 mod p to the n, not just mod p. So the delta Qi's will be cyclic of order divisible by p to the n. And if you map 1 plus Si to, let's say, delta Qi, a generator of delta Qi, then you get a map from your OS to O delta Q, what we denoted by lambda Q, onto whose kernel is just this B. So our task is to prove that with cleverly chosen Qs, and we'll put more and more restrictions on the Qs, you can meet all these conditions in the commutative algebra lemma. Now, the conditions naturally fall into two types of conditions. Well, first of all, the first condition that I wrote up there becomes simply the condition that we already verified, that R is obtained from RQ by dividing by the augmentation ideal. Okay, so the first condition is okay, right? That this is the kernel of RQ to R is okay. This is what we wrote before. Now, the remaining conditions concern R and T, but they're of different nature. The condition on T says that it has some regular control. We have some regular control over the TQs as the Q varies, or that they are large in some sense. And the condition on the R's, the two conditions say that they are small in some sense. So in the remaining time today, I will outline the condition on the T's, and tomorrow we will discuss the condition on the R's. So what we want to prove is proposition 1. For any Q as above, TQ is finite free, finite flat, over lambda Q of rank equal to the rank over O of T. Sometimes I forget the boldface T. Okay. Now I have about 15 minutes. Let's see if I can outline the proof. Let's go. Okay, so let us put gamma q tilde to be simply gamma 0 of nq. And similarly, t tilde q and m tilde q will be similarly defined simply without the Nabin-Tippus, the diamond operators. And of course, we have tq mapping surjectively to tq tilde. And recall the multiplicity 1 theorem, or the one that goes into the Gorenstein, that the Tate module of JQ localized at MQ and the singular cohomology groups of XQ coefficients at localized at MQ plus minus with respect to complex conjugation, which is also H1 of YQ. By this I mean the open affine curve, the affine curve X of gamma Q without the cusps O plus minus MQ are free over Hecke of the respective dimensions, and similarly for gamma q tilde for the other objects. Now the proof of that theorem is till Wynne emphasized, as well as the fact that here, when I localize at MQ, I can replace the full modular curve by the open modular curve, rely on the fact that MQ is non-Eisenstein, or that the representation rho bar that I begin with is irreducible. So the first lemma says that TQ tilde is actually T, by which I mean T empty. Okay, now of course, when Q is empty, there is no difference between the tilde and the non-tilde objects, right? I mean, you don't have diamond operators away from Q. And, well, why is this so? So the proof goes in 2 steps. Okay, this really means what? This means that if you are in gamma naught situation, then after you localize at this particular MQ, that comes from initially from a form that has no Q's in it, then it has no Q's in it, indeed. And this is a statement about congruences between modular forms. It's really a statement that there are no congruences between forms that are old at Q and new at Q in the corresponding J tilde Q. I didn't write it. There's a J tilde Q here. And this comes from the fact that alpha Q is not beta Q. So let me quickly write the proof. First of all, the fact that alpha Q is not beta Q and the fact that Q is 1 mod P, that's enough, not mod P to the n, imply that if you take the Tate module of gamma naught and Q localized at this ideal, this is old at Q, at all the Q's, dividing Q. And the reason you can prove this in 2 ways, I don't have enough time, I'll just say, really there are 2 proofs in the Wiles paper. One proof, along the lines of Ken's talk perhaps, is that if, you see, when you look at the new forms that contribute to this, if there is a new form that contributes to this local component of the Tate module, which is new at Q, then its associated representation is what is called spatial, or is what Ken said last time. It has restricted to the decomposition group at Q. It has omega, beta, and star. But you see, omega gives the Frobenius at Q the value Q, which is 1 mod P. So you don't see it mod P. So the 2 eigenvalues, the 2 betas, will be the same mod P. And we assume that the 2 eigenvalues of Frobenius, alpha Q and beta Q, are different mod P. Okay, so the spatialness of the new form is the thing that gives you. In fact, this is the argument that Wiles gives, but in chapter 2, he does more than that. He does a computation that actually computes the modular fusion between old and new in this situation, really computes the order of the finite subgroup of the Jacobian, which is the intersection of the old part with a complementary abelian variety. And under these assumptions, you see that that number is 0. Is 1, I guess. OK, so that's one step. Now, this doesn't quite finish the proof, because it only says that this is old. So we know now that the Hecke algebra that we want, T tilde Q, is old. Now, the old, well, let's just pretend that we have only one Q for lack of time. This is the T that we want with a variable UQ, and via the theory of old forms, the old theory of old forms, of Aitken and Lanner, I guess, you have that the UQ satisfies, this variable satisfies the UQ squared minus TQ UQ plus Q, or Q, diamond Q if you were in, equals 0. And now, this is the equation whose roots mod the maximal ideal where you localize are alpha and beta. And alpha and beta are distinct mod M. And in my ideal M, I included U minus beta. So this automatically says that this breaks after you localize, and before you put the U minus beta into simply direct sum of 2 local rings, and localizing further at U minus beta just chooses one of them and kills the other one. So this is isomorphic to T. Again, because alpha Q is not beta Q. So this argument is very important, and that's the reason why, to begin with, we made this choice. Not to get any interference between the old parted Q and the new parted Q. Okay. So now, I don't want to erase the multiplicity 1. We don't need this anymore. Okay. The next idea is that it is easier to work with singular cohomology, this guy, rather than with the Hecke algebra, because you can use complex uniformization and some knowledge of the fundamental group of that modular curve, at least as far as you're interested in the structure over lambda, over the diamond operators. So thanks to the fact that this is free of rank 1 over Hecke, instead of proving what we want for Hecke, we can prove it for this, and we can choose between the eigenspaces. I want to choose the minus eigenspace for complex conjugation. So it's enough to prove the proposition, enough to prove the following proposition, that H1 YQ O minus is free. And here, in fact, I do not localize. It's for the minus space, it's true even with before localizing, is free over lambda of rank equal to O rank of H1. It's the same thing, but with a modular curve x, y0, x0. Okay, so this is with the delta Q Nebentipus, and this is a gamma naught situation. And of course, what would this mean? This would mean that it is free over lambda, lambda Q, and after you mod out by the augmentation ideal, you get T twiddle Q, right? But T twiddle Q is just T, so that's exactly what we want. Okay, so combined with the first lemma, this will prove the structure, because as a Hecke algebra, this is the same as it's free of rank 1. Okay, so the proof goes like this. First, you pretend. Any proof that starts with pretend has an unfortunately at the end, but we will deal with this. That gamma twiddle Q had no elliptic elements, was torsion free. In this case, gamma twiddle Q is the pi 1 of YQ of the open curve. Since it's an open curve, this is free. Whoops. This is free. Now, you can compare H1 YQO, of course, well, YQ, all the better, it doesn't have any elliptic elements. Okay, it's a subgroup of gamma Q doesn't have elliptic elements, right? It's a subgroup of gamma twiddle Q. So you can compare this with H1 gamma Q O, and okay, so this is standard. And here you use Shapiro's lemma. That's a group cohomology. You can use Shapiro's lemma, which tells you that this is the same as H1 of the bigger group, gamma twiddle Q, with induced representation, which just happens to be O delta Q. Now, if you check how the diamond operators act here, the action of the diamond operators here gets translated to the action of gamma twiddle over gamma, which is delta, here, and here it gets translated to the obvious action on coefficients. Now, H1 is nothing but C1 over B1. Cocycles over coboundaries. Now, a cocycle on a free group is simply determined by where the generators. And then you continue the cocycle on any word in the free group. And this is a free group. So the cocycles Z1 are free over lambda q. This is lambda q. So is their minus part. P is not 2, so we can decompose. And lambda q is a local ring, so it's a projective, so it's free over lambda q. The B1, you just check how complex conjugation acts. The B1 happen all to lie in the plus part. Anyhow, it's a very small portion of the Z1, but B1 are all plus for complex conjugation. So H1 is minus is isomorphic to Z1 minus, which is therefore free over lambda q. And this would finish the proof if this had no elliptic elements, or if you want, even in the presence of elliptic elements, if P was not 2 or 3, but unfortunately we need 3. So, well, there's a standard trick of rigidifying the situation. I'll take 3 more minutes to describe the trick, and then I'll finish. So part 2 of the proof is the unfortunately. There are elliptic elements in general. So you introduce an auxiliary prime. I think that Taylor and Wiles call it R. And you make the same groups, but intersect them with gamma 1R, introduce gamma 1R level throughout. And R should be larger than 5 to rigidify the situation. And then you can prove the same type of theorem, but not for the Hecke rings that you wanted, but for the Hecke rings with this extra level at R. And you want to choose R in such a clever way so that you, after you localize the maximal ideal, then you get back, fortunately I have the lemma, that you get back the Hecke algebra that you started with. So you see, previously we had exactly the same problem here, and this was the passage from no level to, no q in the level to q, gamma 0 q in the level. And thanks to alpha q not equal to beta q, they were the same. Now in this case, q was 1 mod p, so there was quite a lot of congruences between the gamma naught and the gamma 1 q. And this is exactly what we are exploiting. Fortunately, there is these congruences. But here you don't want congruences not from the level without R up to gamma naught R, and not from gamma naught R to gamma 1 R. And it's pretty easy to see that what you need on R is that 1, in this case, alpha R, beta R, and R itself, which is alpha R, BR, are 4 distinct numbers. In K, you see that alpha R is different from beta R will give you no congruences up to the gamma naught, and that R is not 1 will give you no congruences between gamma naught and gamma 1. And the fact that this can be achieved is a lemma of Diamond and Taylor that is somehow split between their 2 papers, right? But in fact, in the case where P is 3, for example, you can do it by hand. Luckily, of course, you need 4 distinct elements. K is going to be F9, not F3. Of course, it's going to be an element R whose Frobenius is non-diagonalizable over F3. So this sketches the proof of what we want about T, and tomorrow we will do what we want about R. So sorry for going over time. Thank you.